Now we're really going to get to the phrase, the ends justify the means. And hopefully you'll think my ends justify my means. So we're going to look at the means of several samples. And this is the parent population here, which is a normal distribution. You can find the simulation right here at Online Statbook. All right. And basically, what I'm going to do is take some samples. I'm just taking 2 at a time. And I'm taking the average of 2 samples. So where do you expect the averages to average? What would be the average of the averages? So that's how we're getting really different in this chapter. Do you really think I'm going to have an average way down here in the bottom? Probably not, because it would be hard to actually get 2 samples in this lower end. So what happens is it's less extreme. You'll notice that this curve is slightly narrower than that curve. All right, and that was just with n equals 2. So now let's go ahead and do it with n equals 10. So I'm taking 10 samples, and then I get the mean. Take another 10 samples, get the mean. I'm starting to get a little impatient. Maybe I should just start hitting more samples pretty soon. So you'll notice this looks a little tighter than the last one, doesn't it? And I start adding points, and now I'll go to 10,000 and 100,000, and it pretty much fits a normal distribution, all right? And so let's take a look when n is 25. So, oops, back up. Forgot to hit play. So when n is 25, you can see it takes a little longer for my samples to drop. So I'm going to take the average of 25 means. The probability that I'm going to get an average over here means all 25 samples would have to be kind of roughly in this range. So the center still is the same as the mean there. And you can see that the spread is much narrower. So what do I mean by that? Well, look at this. Here is the parent population, right? And here's the distribution of means when I took the mean of 2 samples. Now when I did 10 and when I did 25, you can see that it narrows. So the mean seemed approximately normal, but so is our population. So that kind of makes sense. The variance decreases, the spread, as n increases for larger sample sizes. And the average of the means is approximately the mean of the population. So the means are the same. If you go look over here and try to measure it over here, it should look in the same, like it's in the same spot. Okay, so how do we use this statistically? So the mean for the distribution of a sample mean should be very close to the population mean. That should be kind of intuitively obvious. N is the number of sample means recorded. So it's not n is in my sample. When I calculate a mean, I'm getting n means, all right? So I'm going to do the mean of the means, which means, oh, is there enough means in that? Which means that to find the mean of the means, I'm going to add up the means and divide by how many means I took. And that should be very similar to the population. All right, now let's take a look at standard deviation. It's a teensy bit more complicated here. All right, now they call it standard deviation sigma of x on your math chart, so that's fine. Standard deviation for a mean. So recall, I'm doing the means of the means. So we will need to do, because these are different samples, we will need to do different, we'll have to do Pythagorean theorem for standard deviations. Now, because the population is the same, we're going to basically use the same standard deviation parameter. That does stay the same. And individual sample standard deviations will vary, but I'm not too worried about that because the population is the one we really want anyways. So, doing Pythagorean theorem of standard deviations, remember, in this operation, I'm dividing by n. So I would take my sigma, divide it by n, but I have to do it for every single sample and square it and add it. Well, how many of these do I end up with? Well, I can first of all rewrite this as one fraction. So I have all these sigmas are squared over all these n squared. And I have n of these, right? Because I'm doing the mean of n of them. So n times sigma squared over n squared. These two simplify. And the square root of sigma is just sigma. Square root of n is who knows what. So it's square root of n. So that is the formula on our math chart. The mean is the same, and the standard deviation, you divide by the square root of n. So the nice part is that as you take a larger sample size, your standard deviation or variance decreases. And it's the standard deviation change is inversely proportional to the square root of n. You can't say, oh, I'll make it twice as small by doing twice as large a sample. You'd actually have to do 4 times as large a sample to do that. All right, so that is the part of the math chart we're using. You notice this is, if x bar is the mean of a random sample size n from an infinite population with mean u and standard deviation sigma, then. All right, now if a simple random sample is drawn from a population that has a normal distribution like we did, there's not a lot you have to do. X bar will basically be approximately normal, even for a smaller sample size. As n increases, the spread or variance decreases. The 10% condition still applies. So let's go ahead and look at SAT scores. So we're interested in the distribution of possible means from samples of SAT scores from 20 students. SAT scores have a mean of 500 and a standard deviation of 100. And since the SAT is standardized, it is reasonable to assume that the model for all SAT scores is approximately normal. So I'm going to pull out my numbers. Mean is 500. Sigma, oh, I always have to correct something, don't I? Sigma is just 100, not 1,000. And n is 20. All right. It is reasonable to assume that the SAT scores of 20 randomly sampled students will be mutually independent, provided they weren't all from the same school, right? Because, you know, some schools do have a population that tends to score higher. Also, 10% condition, 20 is definitely less than 10% of the population, so that's fine. So there's not a lot of assumptions we have to do when we're dealing with the normal population and we're looking at the means, all right? So don't forget, there's our math chart. We should go ahead and find the standard deviation. In this case, it's going to be 100, not this 1,000, bad teacher, over square root of 20, square root of n, which is approximately 22.36. They want to know the distribution of possible means. So you're going to be doing a model. It's going to be a normal model with a mean of 500 and a standard deviation of 22.36. And you draw it, put in your 3 sigmas, and put in your numbers, use 1 standard deviation, and this is how you would describe it. According to the normal model, we expect 68% of the samples of 20 students to have mean SAT scores between 477.6 and 522.4. Now, if they had some sort of units on these scores, I would be sure to include those. 95% of samples have means, we expect them to have means between 455.3 and 544.7. You notice how I corrected myself there where I said have means? I said no, to have means, because I don't know that they will have means. I just expect them to have those means. And then 99.7% of samples we expect to have means between 432.9 and 567.1.